Can we start? Yeah. Testing 1, 2, 3. Okay. So let's just get started. I will hope some more people will join. It's a small class. But let me start with announcement. So there is a exam tomorrow. All of you probably know that. It's going to be in Bartlett Hall, room 65. And as I had mentioned, it's a closed book, closed notes exam. But on the weekend, I had posted a note on Piazza saying you can bring a 1-page handwritten, okay, cheat sheet. What you can write whatever you want on it and bring it. So you don't need to, if you think something is hard to memorize or something, you are welcome to write it on 1 page of paper, bring it, and then you have to attach that to the exam book and turn it in, right? So other than that, you can't bring any other material. Okay? So 1-page cheat sheet we will allow, so you don't really feel the pressure to memorize lots of things, all right? So that's the first announcement. The second thing I wanted to mention is I'm hoping to hand out the homework solutions and the homework grades, just so that you can see how you did. And as I had mentioned on Piazza also, the exam questions have similar flavor to homework questions. So by this time, you should have some idea of what type of questions to expect. So for that reason, I'm making sure that we'll try to get the grades out today. Sample solutions we'll post shortly after class to Canvas, so you should have that. Okay. So, and if there are any questions, you should let us know. The last thing is, once the exam is done, you still have the lab due. Remember that is due on the 1st of every month. So the lab is going to be due 1st April, and the last lab is going to be due May 1st. All right. So keep all of those things in mind. So what we'll do today is to continue the discussion from last time. If you remember, last class we were talking about clock synchronization. We talked about GPS, and towards the end of the class, we were talking about this notion of a logical clock that allows us to reason about ordering of events without actually using a real clock, without assuming any clock synchronization. Okay? And towards the end, we said that what logical clock gives us is if there are two events that have occurred in a certain order, the timestamp that the logical clock algorithm gives it will make sure that the one that happened before has a lesser timestamp than the other. Okay? But what it doesn't have is the opposite property, where by looking at timestamps, we can reason about ordering of events. That we'll look at today using vector clocks. And then I'm going to talk about another technique for solving a slightly different problem, which is called distributed snapshots and termination detection. And towards the end of the class, if we have time, we'll start talking about leader election. Okay? So that is the agenda for today. Let's start with the Lamport's clock. But before we do that, I want to give you a new concept which we have not completely discussed, which is total ordering of events. Okay? What we discussed with logical clocks allows us to give what's called a partial order of events. Certain events that are ordered by message passing get ordered, okay? Because the send of a message is always happens before the receive. All the events before the send and all the events after the receive get ordered. But any other events that are occurring in this processes are not going to get ordered. So here are some examples here. The y-axis is time. Okay? There are 3 processes, P1, P2, P3. They all have events A, B, C, D, E, F, G, H, I, and so on. Okay? So the lines that go between processes are messages that are going back and forth. So you will see that B and F are ordered because B is the send and F is the receive. Message must always be sent before it's received. So that gets ordered. As a result, event A, which is before B, and all the events after P2 get ordered because of transitive properties. Okay? But if you look at E and C, okay? E is in process P2 and C is in process P1. They are not ordered because there's no message that has gone from P2 to P1 that allows us to order this. So from our perspective, they are concurrent events. We cannot say which one has occurred before which other one, because there is no real timestamps here. So we are not using real clocks to assign timestamps, so we don't really know what order they occurred. So this is going to give us a partially ordered relationship. Okay? Now, if you want to take a partially ordered set of events and just make it totally ordered, we can just impose some arbitrary tie-breaking rules that say if you have partially ordered events, use some way to order those events. So what we will now do is we will essentially assume that numerical IDs that you have, logical clock IDs that you have assigned to events also dictate a total order. Okay? Even though they're not really total order, we are just going to say when we don't know, we'll arbitrarily assume some order. Okay? And so that's the order and that we will assume, even though that may not be the real order because we don't really know. It's only a partial order. Okay? So in this case, and furthermore, we will append the process ID to the timestamp. Okay, so the timestamp here, which were 1, 2, 3, 4, will become in process 1, P1, will become 1.1, 2.1, and so on, because you appended the process ID, okay, after the decimal place. Okay, so now the clock values are essentially real numbers. So this is clock value 1.1, 2.1, 3.1, and so on. Okay, here also you do the same thing. So you will see the clock values become 1.2 to 3.2 and so on, and 1.3. So this gives us a tie-breaking rule. If there are two events with clock 2 in two processes, okay, so you would not know what the ordering is. Okay, but now because one of them will be 2.1 and the other one here, let's say, is 2.3, you will say 2.1 is less than 2.3 numerically. So we'll just assume that's the order, even though you will see that 2.1 and 2.3 have no relationship. There is no message passing between those two processes for us to know the real order. We just made a tie-breaking rule and just assigned an order. Okay? So you can take Lampert's clocks, okay, which give us a partial order, and then you can just use this technique that just imposes an arbitrary total order. It's not a real total order because we don't know the order for certain events, but we just made up a rule saying this is the way we are going to order events, and all processes agree on this, so we just derived an order. Okay? So this is a simple technique where you can take the logical clock approach, okay, and then assign an ordering to it. Now you might say, why are such ordering important? So here is an example of why the ordering might be needed. Okay? So this is an example of a database. Okay? So here you'll get to totally ordered multicasting later, but let's just think about why total ordering even matters. Okay? So here is an example where you have a database. Let's say it's a bank database. Because the bank has important information, they make a copy of the database. So there is a replica. Okay? So here you have one copy. Here is the two disks represent the two copies. Okay? And let's say users are making queries on the database or making updates. Maybe they're depositing money in their account or withdrawing money or something like that, which updates the database. Okay? Because the database is replicated, you want the state of the database to be consistent across the two replicas. You don't want one replica to have some different data than the other replica. Then your database has gone out of sync. You don't know what is the actual data that you should trust in the two replicas. So the two replicas have to be consistent. Right? The way we are going to enforce consistency is to say that each update that you make to the database, okay, or all the updates that you make to the database have to be in the same order on both of the two replicas. Okay? So that if you start from a certain state, if you have the same set of requests that you process in the same order, you will end up with the same state by definition. Right? So maybe you start with a certain state and you say deduct $10 from account 1. Okay, you do that, and then the database are again in the same state after the replica. And you do another query, they will be in the same state. But if you do things out of order, you may go out of sync. Okay? So for example, if you say I withdraw the money first, and then I calculate the interest for the month on the remaining balance, okay, that'll give you some state. But if you do them in the opposite order in the other database, you first calculate the interest and then withdraw the money, you may have a different interest that you end up with, and so the bank balances will differ in the two cases. Okay? So you always want, when you have database replicas, for the request to be processed in the same order. Okay? Now with that background, let's now look at the two replicas and see what is happening. There are two users that are shown there. Okay? The user to the left is closer to the first replicas but further away from the second replica. this user is closer here and further away from the rest other one. Okay? So let's say they both issue some update to the database, more or less at the same time. Okay? Every query is sent to all replicas because you have to do the same operations on all the replicas. But it's so going to happen that this user's query is going to arrive here first, and this takes much longer over the network to go here. Okay? And this user's query is going to arrive at the second replica first, but takes longer to arrive at the second replica. Okay? So if you just look at the order in which requests are arriving to the database, these two requests are going to arrive in two different order at the two database. In particular, users one request will arrive here first, and users two requests, even though it was issued more or less at the same time, took longer to come over the network, so arrived later. Okay? It's going to arrive at the other end in the opposite order. Okay? So now if the database simply processes requests in the order in which they're arriving, you will go out of sync because now you got requests out of order. Right? So you don't want that to happen. Even if requests are arriving out of order, you want to keep the requests or reorder the requests so that you process them in the same order. Okay? This might require you to delay a request before another request that should have been processed first actually arrives. Maybe it's still in transit. So to do all of this, you need to have a total ordering of all the requests in the system. Okay? So this is where the total ordering concept that I mentioned has to come in. So if you assign a total ordering to your queries, okay, and you process the queries in whatever order is dictated by the total ordering, you are going to be good. Okay? So the Lamport's clock technique that I talked about, okay, can be applied here. I'm not going to show you all the details. This was just an example to convince you why total ordering is necessary in some cases. Okay? Because you may have replicas that are far from one another. Okay? Messages take different amounts of time to traverse the network, so they may arrive out of order at different replicas. And processing things out of order, if they're replicas, will make things inconsistent, make the state inconsistent. So you don't want that to happen. Okay? So I'm not going to go into how you can use Lamport's clock to do total order multicasting right now. We'll get back to that later. If you're curious, there's also further details of this example in the textbook, but we will get to this. Okay? What I want to do instead is to, so this is what we'll skip today. We'll get to this later. What I want to do today instead is to talk about vector clocks, okay, which is essentially the generalization of Lamport's clocks. Okay? Just as a recap, we talked about Lamport's clock last time. Okay? I said Lamport's clock are a simple integer. They have nothing to do with the real clock on your machine. Okay? Every time a process processes some event, it's going to take its integer. It's going to increment its integer by 1. Okay? Every time a process sends a message to another process, it's going to piggyback its clock value. Okay? And when a process receives a message, it takes the max of the clock value that came on the message, max of its local clock, max of those two values plus 1. Okay? That's our time stamping algorithm. Okay? And we said what this gives us is if event A has happened before event B, that arrow there between A and B is the happened before relationship, then the clock value that you assigned using this algorithm will be such that clock value of A is less than clock value of B. Okay? A has happened before B, so A has gotten a lower logical timestamp than B. Okay? But what we also said is the reverse is not true. Okay? If I give you two clock values and you look at them, okay, you can't actually reason about them unless you impose some total ordering that I just talked about. Okay? You didn't do that. If I just gave you two clock values, let's say one has clock value 2 and the other has clock value 3, you can't say 2 is less than 3, so the event with timestamp 2 has happened before event with timestamp. Lamport's clock does not guarantee you that property. Okay? Instead, we want to generalize Lamport's clock with an algorithm that actually guarantees that property. If I give you two timestamps, two numerical timestamps, and you are able to say one is less than the other, it's guaranteed that the event with the lower timestamp has happened before the event with the other timestamp. Okay? That property is called causality. Okay? So essentially, we need to maintain causality, and here causality will mean that if A has happened before B, we say A is essentially causally related to B. Okay? There are other causality properties we'll get to later. Just as one example, one is called causal delivery. You're sending two messages, M and N. Okay? And if the send of M, event that represents the sending of the first message, has happened before the event that represent the sending of the second message, then the receipt should also happen in that order. But if you send one message before the other, receive them in that order. Okay, that's called causal delivery. Okay, but there are many other properties. Okay, right now we are just worried about timestamping. We are not worried about enforcing causality or anything like that. So in other words, we need a timestamping mechanism such that the timestamp of A is less than timestamp of B, and A should have causally preceded. A should have happened before B or causally preceded. Okay, so let's see how to do this. Okay, this is going to give us a new algorithm. It's a generalization of Lamport's clock. It looks very similar with some very small differences. Okay, we will now call them vector clocks. Okay, so now what is a vector clock? First, a logical clock or a Lamport's clock was a single integer per process. Okay, each process has its own integer. Now processes are going to keep a vector. Okay, so vector basically represents n integers for n process. So there's one integer per